Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so we're delighted to have Cheyenne tell us about approximating the expansion profile.
Hello, everybody. So today I'm going to talk about the expansion profile of how to approximate an expansion profile of a graph and local graph clustering algorithms. This is a joint work with Luca Trevisan. I'm going to start with motivating the problem, and then I'll talk about the results. So today I will talk about clustering problems. So suppose we're given an undirected graph G that may, for example, represent friendships in a social network, and we want to partition it into good clusters. Okay. Throughout the talk, I'm going to assume that the graph is deregular, but the results would generalize to non-regular graphs. And okay, so I'm going to define it rigorously, but by good partitioning, by good clustering, we mean like a good cluster is a set where it is highly connected inside and loosely connected outside. So let me now define how we're going to measure the quality of a cluster. We're going to use expansion. So for a set S, the expansion of S is defined as the ratio of the number of edges leaving S over the summation of the degree of vertices in S. Okay. Since we assume the graph is deregular, the denominator is just D times S. So for example, here in this picture, the expansion of this set S is 1/5. So the expansion is always between 0 and 1. And if a set has a smaller expansion, it means that it's a better cluster. Okay. Equivalently, you may think of the expansion as the probability that a random walk started at a uniformly random vertex of S leaves it in one step. All right. So is this clear? We're going to use these definitions throughout the talk. The expansion of the graph is also defined as the worst expansion of any set in the graph. This is also called the Esparza-Scott of the graph. Okay. So the Esparza-Scott problem has been very well studied, and there are different variants of algorithms. But let me talk about the Cheeger type inequalities, which would be of interest to us today. So Cheeger type inequalities characterize the Esparza-Scott of a graph in terms of the second eigenvalue of the normalized adjacency matrix. So Alon Mellman and Alon proved that phi of G for any graph is between 1/2 of 1 minus lambda 2. It's at most root 2 1 minus lambda 2. So in fact, this proof is constructive, so we can get a set of this expansion. So this means that you can obtain an order of 1 over root phi approximation to the Esparza-Scott of the graph. Okay. So why this is important? Because this guarantee is independent of the size of the graph. Okay. Nowadays, since we have to deal with massive graphs, it would be very good if we can have approximation algorithms that are independent, with the approximation factor that are independent of the size of the graph. Right? And of course, this algorithm, the rounding algorithm, is very simple. It can be implemented in nearly linear time. So all you need to do is that you need to compute the eigenvector, the second eigenvector of the normalized adjacency matrix, then embed the graph on a line based on the value of the vertices in this eigenvector, sweep this line from left to the right, and find the best cut. Okay? So in practice, people use this algorithm to kind of to partition the graph, and so they use it kind of recursively. First, they find a sort of Esparza-Scott, an approximation to Esparza-Scott. It divides the graph into two. Then they do this recursively on each of the two sides, okay? Until the graph is partitioned into a good cluster. But this may not do well in practice because of these two things. The first thing is that although this algorithm is nearly linear time, you may end up to spend quadratic amount of time for running it, because there is no guarantee on the size of the output set. It could be that after running linear time, you may just end up separating 3 or 4 vertices from the rest of the graph. Okay? So you may have to run this algorithm order of n times to partition the graph. And on the other hand, it could be that many of the small communities are misclassified by this algorithm, because for example, once you do this, you separate this giant component, you may end up misclassifying small communities, because no matter which side of the cut they choose, it doesn't change the value of the cut that you're selecting that much. Okay, so in order to overcome with these deficiencies, Spillman and Teng suggested the following interesting problem, which is called the local graph clustering problem. So suppose we are given a vertex u of interest in a massive graph, and we want to find a non-expanding cluster around u in time proportional to the cluster size. Okay, so for example, think about the Facebook graph, this massive graph, and let's say you want to find, for example, the CS theory as a cluster in this graph. And we are given to us, for example, the Facebook page of Yuval. Okay? So all we can do is that we can go to the Facebook page of Yuval, I don't know if he passed, and we can look at his friends. And then we can go to the Facebook page of his friends and do this again and again, but we are not allowed to jump in this network. So basically the question is, how should we explore the neighborhood of U to find this cluster? And before talking about the results, note that if we can solve this problem, we kind of get rid of this deficiencies. So in fact, we can do the clustering of a graph by running this algorithm over and over, and we know that every time that the amount of time that we spend is proportional to the size of the cluster that we're going to get. So the running time would remain linear. And on the other hand, we know that if we start from some small community, then hopefully we're going to find something very close to it. Okay, so Spillman and Teng answered this question, kind of, and they've proved the following nice guarantees. So I should also mention that they use this algorithm in their nearly linear time Laplacian star wave. So they prove the following. For any target set A, if we are given a random vertex u inside A, then the algorithm will find a set S mostly in A with the following guarantees. The expansion of S is at most square root of phi log cube of n, and the running time is order of the size of the output 1 over phi squared poly log n. Okay, so we call this 1 over phi squared poly log n as the work per volume ratio. This is basically the ratio of the running time of the algorithm and the size of the output. So ideally, if this ratio is constant, then by applying this algorithm, we can have a nearly linear time partitioning of a graph.
Phi is still phi of A.
Phi is phi of A. Yeah, phi is phi of A.
Mostly in A is 1 minus epsilon?
Yeah, mostly in A is almost 1 minus epsilon for some constant epsilon. All right. And also this algorithm is randomized, so they can do this with some constant probability. In fact, they cannot prove that for every vertex in A this is true. They can prove that for half of the vertices in A they can do this. So this result has been improved. So Andersen, Chung, and Lang improved the approximation guarantee to root phi log n and the work per volume ratio to 1 over phi poly log n. And more recently, Andersen and Peres improve the work per volume ratio to 1 over root phi polylog. Okay? All of these results, like the underlying idea for all of these results is to run a random walk in the from U. So basically they search the neighborhood of U by running a random walk, but they use very different techniques, as you can see here. Like Spearman and Tay use the truncated random walks. Andersen, Chung, and Lang use the approximate page rank vectors, and Andersen and Peres use evolving set. So today I'll talk about evolving set process, and we will use that today. So okay, so what do I want to show you from this table? The thing is, if you look at the approximation guarantee of all these algorithms, unlike the Cheeger inequality, here there is a dependency on the size of the graph. Okay, so it has been an open problem. If one can find a local graph clustering algorithm without any dependency on the size of the graph. And that would essentially give you a local variant of the Cheeger inequality, because it would kind of give you the same guarantee as the Cheeger inequality would give you. Okay? So this is basically the subject of this talk, and we kind of solved this problem. So we proved the following. Prove that for any target set A, if we are given a random vertex U in A, then we can find a set S such that the expansion of S is at most a square root of expansion of A over epsilon, and the work per volume ratio is at most A to the epsilon 1 over root phi polylog. Okay? So this indeed kind of provides a local variant of the Cheeger inequality, because both the approximation guarantee and the running time is independent of the size of a graph. It just depends on the size of the cluster that you're trying to find. Okay? Yeah, learning time has up to this polylog. Yeah, I agree. So one more thing is that this algorithm generalizes the previous result, in the sense that here you can choose epsilon whatever you want. So if you choose epsilon to be 1 over log of A, you can replicate the previous results. So in fact, there is a trade-off between the running time and the approximation guarantee. By choosing larger values of epsilon, you would obtain a better approximation guarantee with a worse running time, and by choosing smaller value of epsilon, you would get a better running time and a worse approximation guarantee. Okay, any question? Okay, good. So before talking about the proofs or the algorithm, I want to talk about an implication of this result, which is interesting in the theory community. So there's a close connection between this problem and the small set expansion problem. So let me first define the expansion profile of a graph. Let mu be a parameter between 0 and n-halves. Then phi of mu is defined as the worst expansion of any set of size at most mu. Okay? So for example, phi of n-half is just the sparse cut of the graph. Okay? So small set expansion problem asks if you can find approximation algorithm for this parameter phi of mu, which is independent of the size of a graph. Okay? So by Cheeger inequality, we know that we can do this for mu being n-half. So basically here the question is if you can do that for any values of mu.
So when you say independent of the size, you mean for mu, which is some constant times the size, for any constant. Because mu depends on the size, so I'm not sure what.
No, for every mu. It cannot depend on mu.
All mu at once? All mu at once? I don't know.
Yeah, I give you a mu in the input. You give me an approximation algorithm.
100?
Yeah, it could depend on n. It doesn't matter. But
yeah, but if it depends on n, it does depend on the size of g. N is the size of g, right?
Mu may depend on the size of g, but I want the approximation guarantee to not depend on the size of g. So the approximation guarantee cannot depend on mu, for example. It may depend on phi of mu, but it may not depend on mu. Phi of mu is always between 0 and 1. Yeah. So it may depend on phi of mu. Okay. It could be, for example, some crazy function of phi of mu that, So why this problem is of interest to us. First of all, Raghavendra and Schwerp conjectured that this is an NP-hard problem. So they conjectured that for every value of rho, there exists some delta much, much smaller than rho, such that it is NP-hard to distinguish whether phi of delta n is close to 1 or if phi of delta n is close to 0. And more importantly, they proved that this conjecture improves the unique games conjecture. So in other words, this means that if you want to design an algorithm for the unique games, you should start from the small cell expansion problem. Because this is an easier problem than the unique games. Every algorithm, if you design a polynomial time algorithm for unique games, you would obtain a polynomial time algorithm for a small cell expansion problem.
So in other words, refuting these conjectures. Right.
Yeah, if you want to, in other words, if you want to refute this, you should start by refuting this.
If you want to prove it.
Not for the proof. No, it could be that you could design an algorithm for this one, but not for unique games. But okay, so our result as a corollary imply an approximation algorithm for this problem. So we can prove that for any values of mu and epsilon, we can find a set of size at most mu to the 1 plus epsilon, and expansion at most root phi of mu over epsilon. Okay. So this does not refute the conjecture, because the size of the set that we find is larger than mu. If we could prove, for example, that the size of a S is within a constant factor of mu, then we would have refuted the conjecture.
But what's the running time, though?
The running time is, again, if I have a vertex of this target set, then it's going to be sublinear. It's going to be just proportional to the size of the set. It's basically a corollary of the algorithm. So as I said previously, our local graph clustering algorithm can ensure you that the output set has a large intersection with the target set. So in fact, this gives you the intersection. The output set, like mu to the minus epsilon fraction of the output set, lies in the target set.
I mean, the definition of phi of mu was global.
Right?
In your algorithm, you need to start with a target set.
No,
right?
our algorithm, we can run the algorithm from every vertex in the graph and just find the best set. We don't need to start from a target set. I mean, then the running time would be worse. Yeah, it depends whether. But for here, you don't want to optimize the running time. You just want to find an approximation to the problem. Okay.
This is a different nature result here. The issue is not locality. The algorithm to do this will start from every vertex, so it will have all the vertices.
So I mean, so the idea is that if you have a local algorithm, it's a good hope that you can solve this problem, because a local algorithm will start from the neighborhood of the vertex, and then it expands to all of the vertices. So you may hope that along the way you find a small non-expanding set. So that is why these two problems kind of related to each other. I mean, for example, it could be that, I cannot prove it, but it could be that if we can get rid of this a to the epsilon, then you could have solved the small cell expansion problem. Okay, so this result is also proved independently by Kwok and Lau using different techniques. Okay, so if there is no question, let me go on to talk about the algorithm and the analysis. Okay, so
can you go back? So you said that is still possible, even over there you remove size a to the epsilon.
Yeah. Yeah, it is possible, and in fact, even the algorithm that I'm going to present may do that, but we cannot prove it. I will mention by the end of the talk that the current algorithm, we don't have any tight example for it. It could be that it can refute this conjecture. We don't know. Okay, So in this talk, I put more main focus on this theorem. So I try to forget about the running time. I'm going to show you how we can approximate the small cell expansion problem. Okay, I'll give you some ideas also how we can talk about the running time too. But the main, yeah. Okay. So let me now talk about the algorithm for a couple of minutes, like 10 minutes, I think. So we use the same machinery, the evolving set process that Andersen and Peres used in their work. I will define the evolving set process in a minute, but as I will show you later, the algorithm is, at the end, very simple. We just run this process, and we return the best set that we find. Okay? So what is the process? The evolving set process is a Markov chain on the subsets of vertices in a graph. Okay? So let me tell you how we can. Let me define you the Markov kernel. So for a set S, we first choose a random threshold U uniformly between 0 and 1. Then we include all of the vertices where the probability of going from V to S with a lazy random walk in one step is more than U. All right? So for example, if U is less than 1/2, then the new set would always be a superset of the old one. Why? Because this is a lazy random walk, so the probability of going from every vertex inside S to S is more than 1/2. So the new set would be a superset of the old one. And if U is more than 1/2, the new set is going to be a subset of the old one. So let me show you an example. It would be more clear. So let's say, for example, we want to run this process on this cycle. Okay? So we start from this graph. Let's say the first threshold is 0.2. So we include the vertices that have probability more than 0.2 of going to that single vertex. These vertices has probability 1/4. Right? So we include these two vertices. Okay? Then the next threshold is 0.7. This is not going to change.
You want to throw out the middle one.
So the middle one has probability 1.
Staying inside.
Of staying inside.
No, before.
If it's probability halves, then it's,
The
So-
threshold was 0.2.
Yeah, so
so it's about.
it's above the threshold.
Sorry.
So then the next one is 0.1, you increase again. The next one is 0.8, now you decrease because these guys has probability only 1/4 of going to S. So you decrease the set. Then you again decrease, and then you decrease to empty set. Okay? So it's not hard to see that this process has two absorbing states, either the empty set or the full set. Okay? So since we want to run this process for a sufficiently long time to find a good set, we would like that the process absorb in the full set, in the whole set. Okay? So in order to avoid absorbing in the empty set, we condition on the process to get absorbed in the full set, and we call this new process the volume biased evolving set process. Okay?
So how are you picking the thresholds?
It was uniformly random between 0 and 1. So here is the Markov kernel for the volume biased evolving set process. We just need to multiply the original Markov kernel by the ratio of the new set over the old set. This follows simply by the by the fact that the evolving set process, that the size of a set is a martingale evolving set process, and using the loop H transform. Okay, so let me not prove it, but yeah, this is going to be the Markov kernel for the new. So in the rest of the talk, whenever you use this hat notation, this means the volume biased process, and whenever I don't, this means the original one.
But this probability would never be larger than 1. S1 can be
No, it could be larger.
larger than 1.
S1 could be larger than S.
Then S.
Yeah, the probability would never be larger than 1. Yeah, this follows by the loop H transform. But for example, you may see that this would never absorb in the empty set because if S1 is empty, this is going to be 0. So it for sure never absorbs in the empty set. It may just absorb in the full set. And it's also not hard to see that this is indeed a Markov kernel. So summation of probabilities are 1. OK. So let me tell you the close connection. So as I said, there's a close connection between this process and the random walk process. And in fact, Diaconis and Phil first studied this process in order to compute the mixing time of random walks. Okay? So there in the paper, they prove a very nice coupling between this process and the lazy random walk. So they define this coupling xt-st that has the following properties. First of all, xt is always inside st. So the random walk is always inside the S. And moreover, conditional st being some particular set S, the random walk is uniformly distributed in that set. Okay, so as an example, note that once the process absorbs in the whole set, the random walk is mixed. So what this means that if you want to compute the mixing time of a random walk, you can just run this process and compute the absorbing time of this process.
Upper bound.
Yeah, upper bound. Yeah, upper bound the absorbing time of this process.
So this is regular clocks or?
No. Okay, so also Andersen and Peres in their paper use this coupling to prove that one can simulate the evolving set process. So they prove that for any sample path S0, S1 up to ST, we can simulate this in time essentially proportional to the size of ST. So size of ST times root T polylog A. So in fact, what they do is that they look at the vertex, they do one step of the random walk, and then they condition on the set, on the new set to contain this new vertex and see how it should change. Okay. So the upshot is what this means. This means that okay, you can run this process for a sufficiently long time without being terrified of the running time, right? It is okay. So you just need to prove that the process is good. It's going to give you a small non-expanding set. There is no problem with the running time. Okay. So in fact, our algorithm, we just do that. We just, for a small expansion, we just run this process from every vertex of the graph. And we run each copy once the length of the walk is sufficiently large, at least it's log of mu over phi of mu. And if any of the copies finds a small non-expanding set, then we just return it and we're done. So very simple. We just run the process from each vertex, find the. Okay. So let me now talk about the analysis. I'm going to show you that there exists a vertex V such that if you run this process with some non-zero probability, you're going to find a small non-expanding set. Okay. So before going into the mathematical notations, let me give you a high-level overview of the proof. So the proof uses the following two observations. The first one is that the evolving set process grows rapidly on expanding sets. Okay. And the second one is that the process cannot get trapped in non-expanding sets, cannot leave them very easily. Okay. So it's kind of putting this together. What you would like to say is that okay, the process. So if this is the target set, I want to say the process grows very fast until it hits my target set, then it has to spend some time there. So I should be able to find this target set. Okay, so for example, let's say think about this dumbbell graph. Let's say you have two expanders connected by an edge. I'm going to start the process from this vertex. So you may get some intuition by looking at a random walk. So the process kinds of work the same as a random walk. And we know that random walk in the first log n steps, very rapidly mix in this expander. So the process kinds of do the same thing. It very rapidly expands and covers the whole set. And then for quite large amount of time, he would just add or delete some vertices. It would be very close to A. And then we should be able to find it. We'll be able to find it.
You had it going over that edge.
Yeah. So
once you get someone over there.
no, there is a difference between random walk and so I agree. The random walk, it may take a lot of time for it to hit this vertex, but the process may get increased, but then it would decrease.
Why won't it then expand into the other side?
The reason is that from this point of view, like at this time, you can think about running an evolving set process from a single vertex, right? But if you run an evolving set process from a single vertex, with high probability, it will go to the empty set. This new process is not going to be volume biased anymore because it always has this big mass at the left, right? So for example, if I have this vertex, if I include his neighbors, then the size wouldn't change.
Yeah.
So it's the same as if you were running the non-volume biased process from this vertex. And so with high probability, you're going to
The fraction of the neighbors this vertex has in the set is very small, so it will only be retained in the set next time if the uniform threshold happens to be below this very small ratio.
You add a point if a chance of a step from there goes into the set, above the threshold.
You
Probably
include-
goes into above the threshold, right?
yes.
Include the set if the fraction of its neighbors in this current set is above this threshold.
It's about.
Right.
And so this vertex is very unlikely to be in the set in the next iteration.
It has
Yeah, it has-
at least half because it's a laser.
Well, that particular vertex, this to stay in there, you mean? I was thinking the neighbors of that guy.
Right, to stay, it has, right,
It's a laser random, so
Right,
it has probably half. No?
right.
No, but if you run it a couple of times, then you would lose it.
It's smaller.
But it won't grow because for those guys it's tiny for the on-site there.
I don't see where the neighbors will go into it next.
For each neighbor, the chance for it to go in is very unlikely.
No, I think the right way to think about it is, suppose I just run the volume, not the volume bias, the evolving set process from a single vertex. Okay? Then the process is a martingale. So the probability 1 over n, the process would absorb in the empty set. Sorry, with probability 1 minus 1 over n. The probability would absorb in the empty set, and only with probability 1 over n it would get to the whole set. Now, my claim is, once you get here, then the process this new process, from the point of view of this expander, is just as if you run a non-volume bias process, because you have a giant component at the left, so this ratio is always going to be 1. Okay. So let me now tell you how we can make this quantitative. So we're going to prove the following two statements, and I'm going to show you that this is sufficient for a proof. So the first one is the following. We're going to show that for any time t, if you start the process from some vertex v, for any vertex v, the minimum of the expansion squared of all the sets in the path is at most order of log of st over t with high probability. Okay, so in other words, if for example these expansions are large, then you should have a large set by this time. Right? Now, so again, so this means that if you're going through the expanding set, your sets should grow very fast. But in the second statement, I'm gonna tell you that I'm gonna show that for quite a large time, the set cannot grow very fast. The set should remain small. So here we're going to show that if you choose t very large, something like epsilon log of mu over phi of mu, then all of the sets are small. All of the sets in the sample path are at most mu to the 1 plus epsilon. Okay, so these two basically contradict each other. One of them says, okay, either you find a good non-expanding set, or then you're done, or if you don't, then your process should go very fast. But you know you cannot grow very fast because there is a target non-expanding set. So this means that with some probability, you should grow slowly. So you should be able to find a small non-expanding set. So let me tell you why this proves the theorem. It's very easy. Just plug in alpha equals mu in the top. Okay? Then by union bound, you can prove these both of the things statements occur with some probability mu to the minus epsilon over 2 or something. Then what do you get? From the bottom one, you get all of the sets are small. They have size at most mu to the 1 plus epsilon. From the top one, you get there exists a set of size of expansion at most root phi over epsilon, because put t equal epsilon log of mu over phi of mu, this whole thing is going to be root phi over epsilon. Okay. So now let me tell you how we can prove each of the statements. So I'm going to start with the top one. So first I'm going to show you how we can show the process grows rapidly in one step. Okay? So this is based on observation due to Morris and Peres. So they show that for any set S, if you look at this expectation of the root of the change in one step, it is at most 1 minus phi squared. Okay, so for example, think of the phi being a constant. This means that in one step, your new set is constant times more than the old one.
Why do you have S1 on the bottom?
You should have to. What do you mean?
See, always with respect to the hat process.
Yeah. So this is with respect to volume bias process. You can write it in terms of the non-volume bias one just by multiplying it by S1 over S. And then you get this. Okay? But now, this is not hard to prove. So in fact, the proof simply follows from the fact that the volume bias process is a martingale. The size of the set in the volume bias process is a martingale. So this means, the reason is that if your threshold is below 1/2, your new set would be 1 plus phi more than the old one in expectation. And if it is more than 1/2, it would be 1 minus phi of the old one in expectation. The reason is just follows from the same reason that the probability that the random walk remaining inside the set S is 1 minus phi. Okay, it's exactly the same reason. So having this in hand, you can just prove this using Jensen's inequality. All right? So now how can we use this to prove that, totally, like overall, the set grows rapidly? So let me call this ratio psi of S. This is a ratio just depend on S, right? Now, the idea is to define a martingale. So we define this ratio 1 over root st times the product of the psi functions of S0 up to st. And it is very easy to see that this is a martingale. Because expectation of mt given, S0 up to st minus 1 is, you can write it as expectation of, root st minus 1, root st minus 1 times the psi functions, psi of S0 up to psi of st minus 1, condition on the above. And then, if you take this thing out, it's just mt of minus 1. This thing is, this thing is a psi function. This is mt of minus 1 times 1 over psi of st minus 1 times expectation of root st minus 1 over st. This is with respect to the hat. Okay? It's easy to show. Don't worry about it. So what this means is that, okay, in expectation, this mt is going to be 1. So by simple application of Markov inequality, you can show it's going to be less than any alpha with some large probability 1 minus 1 over alpha. So plugging in the values, you're going to get the following. With probability 1 minus 1 over alpha, the product of 1 over 1 minus phi squared is less than alpha times the square root of st. And if you just take the logarithm of both sides, you're going to get this inequality. So very easy. Okay? So let me now talk about the second part of the proof. So here we want to show that the set gets trapped in non-expanding sets. Okay? So let me instead of proving that all of the sets are small, let me just prove that the last one is small. Okay? And because the process is growing, if the last one is small, essentially all of them should be small. So how are we going to prove that the last one is small? So I want to prove that the last, like for a sample path S0 up to st is at most mu to the 1 plus epsilon with this probability, with some inverse polynomial probability of mu for some very large t. So here the idea is to use the coupling between the process and the random walk. So my claim is this is equivalent to the following. I just need to prove that a random walk started from this vertex v is going to be inside A with some. I need to prove that there exists some set A such that the random walk started from V will going to be in A in t steps with some probability, some non-zero probability mu to the minus epsilon. Why these two are equivalent? Just use the coupling. So you know that, let me recall, what did the coupling say? It said the distribution of the random walk is, it says condition on the evolving set process being equal to some particular set, the random walk is uniformly distributed on that set. Now, if I look at the distribution of the probability that a random walk is in some set A, this is equal to the expected fraction of the intersection of st with A. Right? Because you can easily go from the evolving set process to the random walk. If I just look at the distribution of the sets, I can just apply the uniform distribution on each set and then take the average. This would give me the random walk distribution. Now if I want to look at the probability of being in some set A, I can just look at the set distribution, project it onto the set A, take the uniform distribution, and then take the average. This would give me that probability. Now this tells me the right-hand side is small, but I know the left-hand side is smaller than the ratio of A over st. So because I take A to be small, st can be at most mu to the epsilon more than A. So st can be at most mu to the 1 plus epsilon. So I just need to prove this equation, which is just forget about the evolving set process, it's just a random walk. So I just need to prove that there exists some set A, and as you might guess, this set A will be my target set. So I want to prove that for my target set, there exists a vertex such that the walk is going to be in that set after t steps with some probability mu to the minus epsilon. Okay? So I'm going to prove something stronger. Instead of proving that the walk is at A at time t, I'm going to prove that the walk never leaves A up to time t. All right? And I'm going to prove it with this probability. but these two are essentially the same. If you take t to be epsilon log of mu over phi of mu, then you see these two are exactly the same. So we just want to prove something, some property of the random walks. We just want to show for every set A, there exists a vertex V such that the random walk never leaves leaves A with probability 1 minus phi of A to the t. Okay? So again, I'm going to make it even stronger. I'm going to prove if you choose V uniformly at random in A, it's never going to leave A with this probability. Now this should kind of recall you of a definition of phi of A. So what was the definition of phi of A? It said it's the probability that the random walk leaves A, and 1 minus phi is the probability that the random walk remains inside A. So intuitively, this should hold because if the probability that the walk leaves the set A at each time was independent of each other, you would exactly get 1 minus phi. So we want to say it's even better. So here is some extreme example where you get equality in the above. So let's say, remember that each vertex in A has, on average, d times phi of A edges going outside. Now let's say that's the case for all vertices. So all vertices has exactly this much amount of edges going outside. Then, if you do one step of the random walk, the distribution remains uniform inside A, because everybody has the same number of edges going outside.
The distribution being conditioned to stay in A?
The probability of staying in A in every step.
Yeah, you do one step of the random walk, and look at the distribution remains inside A.
So say your sentence again. What are you saying?
So I'm saying, start from a uniform distribution in A. Now do one step of the random walk. From each vertex, exactly the same amount would go outside. So if you project the probability back to the set A, you get uniform distribution. Or again, if you condition it to be in the set A, that's it. Yeah, conditional probability.
Some vertices may have more, no?
So
Yeah, exactly.
when you say
In this case,
In this
In
case,
this
no,
case, this is
but
a
in general, some
yeah, so-
more and some less.
Yeah, so in general, some vertices might have more. So what we want to say is that intuitively, if some vertices have more edges going to the outside, then this probability, the probability of being on them should only decrease. Because if you are on those vertices, you would certainly leave the set faster. So after some number of steps, your probability should be more concentrated on the vertices with less number of edges going outside. So you should have a higher probability of remaining inside. Okay. So how can we prove this? It's also, again, simple. So let P be the transition probability of the lazy random walk. Then this thing is just equivalent to the following. So let me parse this for you. So U of A is the uniform distribution on A. So we start from the uniform distribution of A. We do one step of the random walk. We project it back. I of A is the identity matrix on the set A. So we project the walk back on the set A. We do one more step, we project it back. We do one more step until the time t, where we just add up the summation of probabilities. And this is exactly that. And the right-hand side is just, this thing t by removing the t. And we know that this is because we know that 1 minus phi is the probability that the one-step random walk remains inside the set A. So I just need to prove this equation. And I can even reduce it even more. So let x be square root of this uniform distribution. Then and also define this PIA to be a matrix Q. Then the left-hand side is just x transpose Q Tx. Right? I can write this square root of x, square root of x. And the right-hand side is x transpose qx to the t by symmetry. So I just want to prove this thing. All right? And this is also simple to prove. So you just need to diagonalize Q and use the fact that it is a positive semi-definite matrix. So you can write X transpose Q of X.
Q is not symmetric.
Yeah, Q is not symmetric, but I can make it symmetric simply by putting another I of A here. So yeah. So I can write X transpose QX as summation of X transpose VI, where VI's are the eigenvectors. So let's say V1 up to Vn are the eigenvectors of Q, and lambda 1 up to lambda n are eigenvalues. Then this thing would be exactly this. Oh, sorry. This is squared. And the right-hand side is just the whole to the t. So we just want to prove this thing is more than bottom one. And this is, again, simple to prove because this is just Jensen's inequality. These eigenvalues are non-negative. The summation of these guys add up to 1 because X is a unit vector. So this is just Jensen's inequality. All right. So I'm almost done. So in fact, this equation holds for any x and q. So let me finish the talk. So again, we proved that for any mu and epsilon, our algorithm can find a set of size at most mu to the 1 plus epsilon and expansion root phi over epsilon. This has been the first approximation to a small expansion problem without loss in the expansion. So previously, there has been many works, even with many people in this room, where they could give an approximation algorithm with preserving the size of the set, the size of the target set, but losing in the expansion.
You're missing a log in the second.
This one?
Yeah.
No, it's log of n over mu, log of n.
It's a log n cancel.
No, sorry, this log n is not in the denominator.
It's log squared n.
Yes, log is, yeah, no, yeah.
There's a bracket around n over v.
Yeah, there should be a bracket here. And also we proved that a Cheeger cut can be computed in almost linear time in the size of a target set, and thus obtaining a local variant of the Cheeger inequality. Okay. So let me give you some open problems and finish the talk. So perhaps the main interesting open problem is if one can find an approximation algorithm for phi of mu that is independent of the size of the graph. So in particular, this is a nice question. If you can prove that with some inversely polynomial probability in mu, all of the sets in the sample path of the evolving set process are at most order of mu. So here we prove that they are at most mu to the 1 plus epsilon. And we managed to get this size, mu to the 1 plus epsilon of the output set. Now if you can improve this to order of mu, then you would refute the small expansion conjecture. Okay. Another open problem is that, so these works, they all use the semi-definite programming relaxation, not the random walk. It also would be interesting if one can kind of replicate our results using the semi-definite programming relaxations. It would, it may highlight some new ideas for the problem. In terms of the local graph clustering problem, one interesting question is if one can generalize these to weighted graphs. Currently, we don't know. None of the algorithms would generalize to weighted graphs. And The other one is that, if you use the traditional spectral clustering algorithms, as I said, you may misclassify the small communities. But here, since you can, using local graph clustering, since you can run the algorithm from every vertex in the graph, you can hope to find overlapping communities in a network. But so there has been, although there is quite a lot of practical interest in this problem, there hasn't been much of the theoretical works. And it would be a very interesting direction to work on. Okay, thanks.
So what do you mean like for this using SDP relaxation? For example, can you get Cheeger kind of bounds for using SDP relaxation?
Yeah. So this result, they use SDP relaxation. And if you don't want the set to be large, you can just plug in mu to be n½ and then you get Cheeger inequality. But then there is no guarantee on the size of the set. It could be very large.
So about weighted graphs, didn't you say at the beginning that you didn't need regular graphs?
We don't need regular, but we need unweightedness.
Multi-graphs? They have to be simple graphs.
Yeah, we need it to be simple graph.
So it needs to be simple graphs.
Yeah.
Why?
I mean, it's not so clear how you should. So all of these algorithms kind of depend on the number of edges in the graph. But do you have a better answer?
If you just interpret, again, the weights are conductances, and you just interpret them as multiplicity of edges.
Okay.
Just run the very same.
No, but you can run the algorithm, but can you bound the running time?
Again, it will bounds, the easiest bounds will involve this volume, so it will involve the weights.
Yeah.
Maybe.
I mean, the point is, it might be that the analysis would work. None of the people have done this, and I haven't. I don't know if it is. There's an inherent difficulty on the problem or not.
If the graphs are directed, that's a whole different.
Yeah, of course. If the graphs are directed, it's much more difficult.
So then you mean for weighted graph, if the weights are small, it's the same? Integer and small, let's say.
Yeah, then it's exactly the same. You can just, if you want to interpret it as multiple edges and run the algorithm exactly as it is, there's no difference. If the weights can be very large, the algorithm still works. It's just a matter in the analysis.
Yeah, that is why I don't know. If you may have very large edges versus very large weights versus very small weights, then yeah, I don't know. It could be that analysis works.
So it would affect the running time.
Yeah, the running time, but the approximation guarantees would work, of course.
Any other questions? Russ, you have another? No, thanks.